So in this lecture, we're going to examine sp3 hybridization. So let's define it. Well, this is defined as simply the combination of 4 atomic orbitals in a given atom to produce 4 hybridized orbitals, which then can interact with other atomic orbitals of other atoms to produce covalent bonds. So to show this, let's examine the following methane molecule. So our goal will be to produce this methane molecule composed of 1 carbon and 4 H atoms. So the carbon has the following electron configuration. It has a total of 6 electrons. 2 electrons go into the 1s, 2 electrons go into the 2s, and 2 electrons fill the 2p. Now each H atom has 1 electron each, and that means that electron goes into the 1s orbital. So we have 1 valence electron per H atom and 4 valence electrons, 2 plus 2, 4, for the carbon atom. Now, before the carbon can combine with the H atoms to form our methane, hybridization must take place. Remember, hybridization occurs because it increases the volume of the lobe interacting with the other atomic orbitals, and this increase in overlap will increase the strength of the bond. So hybridization takes place so that there is a better overlap between atomic orbitals, and this stabilizes the bond. So before hybridization took place, we had the following picture of our carbon atom. So the carbon atom has 4 valence electrons. 2 valence electrons are in the 2s orbital shown here. 1 valence electron is in the 2px, 1 valence electron is in the 2py, and no electrons are in the 2pz. So, how does hybridization take place? Well, first we must ask the following question. How many hybrid orbitals should carbon develop so that it can create the methane molecule? The answer lies in this picture. How many bonds are created between the carbon and the H? Well, since we have 1 carbon and 4 H's, there are 4 bonds. So that means we need 4 hybrid orbitals. So that means we have to use the 2p, the 2s, and all the 3p, x's, y's, and z's to form our 4 hybrid orbitals. In other words, for hybridization to take place, the 2s must combine with the 2px, that must combine with the 2py, and the 2pz. If we combine all these 4 atomic orbitals, we will get 4 hybrid orbitals that are all identical and look like this. So we get 4 sp3 hybridized orbitals in which we have 25% s character and 75% p character. So this guy undergoes hybridization. We get the following depiction. So now our carbon atom no longer has that individual 2s and these individual 2px, 2py, 2pz's. Instead, we have 4 identical sp3 hybridized orbitals. And since we have 4 valence electrons, each valence electron goes into each of the 4 identical sp3 hybridized orbitals. So 1 goes into here, 1 goes into here, 1 in here, and 1 in here. Now the carbon, which has undergone hybridization, is ready to interact with 4 of the 1s orbitals. So here we take the 4 1s orbitals, we place each onto the positive green lobe, and we get our methane molecule. So a simpler way of looking at it is via this black diagram. So here we have our carbon nucleus. We have these sp3 lobes, which each have an electron. They interact with a 1s orbital, so H with 1 electron. They bond, and we create the following picture. Notice that these guys are identical. Now, For our methane molecule, experimentally, we know that the bond between any two, CH and CH, is 109 degrees. And this takes the form of a tetrahedron. So now let's look at the energy diagram. So let's say we want to combine one of these 1s's with the sp3 hybridized orbital. So the 1s will be slightly lower in energy than the sp3. The sp3 will be slightly higher. They will combine to form a bonding and an anti-bonding orbital, or a molecular orbital. So here we have the bonding, and the electrons will go into this orbital. And here we have the anti-bonding. Electrons will not want to go into this orbital. They will stay in this bonding orbital. And so this is exactly what happens in this picture, except this happens 4 times.